This conference will now be recorded.
So, very good evening, students. We were discussing on wave optics, interference, and diffraction. This part. So here, as I have discussed already, that we are solving JEE mains exam paper on this particular topic. So mains and whenever possible, we are taking up JEE advanced question also. But anyway, we will be taking up the advanced questions further again in detail. So today we have picked up few questions on interference and diffraction mixed problems. So let us solve these problems. So here in this problem, it is stated that consider a Young's double slit experiment as shown in the figure. What should be the slit separation D in terms of wavelength such that first minima occurs directly in front of the slit S1? Okay, so you can see this figure. In this situation, see, first of all, what is the condition for minima? We know the condition for minima is the path difference. If the path difference is delta x, okay, so delta x is equal to lambda by 2 for first minima. Okay, so then we have to find out path difference. So here you see in this diagram S1, this is S2, and this is actually D, and according to our figure, this is 2D. So look here, if I say this is P, what will be the path difference? Path difference will be delta x is equal to S2P minus S1P. So this we have to find out, and then we can equate to this lambda by 2. So what is S1P and S2P? Look from this figure here, the same figure I have drawn here. So this is D, this is 2D, and this is P. So S2P, S1P, anyway we know S1P is 2D. What is S2P? S2P is the, see, if you just think of a right angle triangle where this is the 90-degree angle, so this is hypotenuse. So in that sense, it will be, this square square root of 4d square plus d square. So it would give you root 5d. Okay, root 5d. Now if we find out what is the delta x will be S2p minus S1p. So what is S2p? S2p is square root of 5d. What is S1p? S1p is 2d. Then see, from here we can take up d common. So square root of 5 minus 2 whole into d. So this is the path difference, and for first minima to occur over here, we have to write down this path difference is equal to lambda by 2. So if we excuse me, so if we write it here, so this path difference, that means root over 5 minus 2 whole into d. If this is equal to path difference lambda by 2, then what will be the slit separation? So that is what was the question. So slit separation D will be lambda by 2 into square root of 5 minus 2 this. So you look here, there are options, lambda by this. So this is the correct option in this problem, lambda by 2 4 into square root of 5 minus 2. So this is the slit separation. Okay, now we'll move on to this question, second one. This is also from Young's double slit experiment, and you know, as you can see, these questions are from actually JEE Mains 2019. Maximum questions are taken from there. Now let us read this problem also and try to solve it. So in a Young's double slit experiment, the slits are separated by this much apart, and light of wavelength 500 nanometer is incident on the slit. The total number of bright fringes that are observed in the angular range. So you know, we have to find out how many numbers of fringes will be there within this particular angular range. Okay, so to solve this problem, what we have to do is, we know that d sine theta is equal to n lambda for first minima to occur, bright fringe to occur. So 2d sine theta, so this is constructive interference. D here, slit separation is D, so I'm writing D, or you may write 2D also. So D sine theta is equal to n lambda. N is the nth order fringe, nth order fringe. Okay, this n is the order of the fringe. So D sine theta is equal to n lambda. Now we can write D is this much, this is millimeter, so I can write into 10 to the power minus 3 d sine theta. So you know, for theta is equal to 0 to 0 to 30, within this range, we can apply the formula d sine theta is equal to n lambda. So this is the sine theta is equal to, take half. Okay, the sine theta, n is the one we have to find out. Okay, so n we have to find out. Here this lambda will come. Lambda is again 500 nanometer. So then you know, n is equal to, this is suppose n1 for the half of the range, 0 to, this is theta, 0 to 30. That means in this range, the number n will be 0.320 into 10 to the power minus 3 divided by 2 into 500 into 10 to the power minus 9. Okay, so this would give you nearly 320. Okay, so let us say this is n1. You can just do the calculations. So for the other half, that means theta less than 30 less than 0. In this range, what will be the number of n2? Similar thing here also, n2 will be 320. Now if this is the case, actually this is the case from, see, this is 0 to 30. That means if I take this as 0, then here will be 30. So this part and this part. Now minus 30 to 0, this part, okay, minus 30 here, suppose minus 30 to 0 here. So this part, so there will be, see, central bright fringe and the number of fringes, this 2. So total number of fringes will be observed in this range. Total number of fringes will be 320 plus 1 plus 320. So which is 641. Okay, so this is how we get this total number of bright fringes that are observed in the angular range. This is 641. Okay. All right, so we have got the second question answered. Now we'll try to find out the third question. So the third question, okay, I have not given the options, so I'll give you the options here. In a Young's double slit experiment, if light of 500 nanometer is used to produce in distance pattern, when the distance between the slits is 0.05 millimeter, angular width of the fringes formed on the side of the screen close to. So you have to find out the angular ranges. So how to find out the angular range? We'll just solve it. Let me just give you the options for this question first. Yes, the options are 0.17 degree. Option B is 0.57 degree. C is 1.7 degree. And option D is 0.03 degree. Okay, these are the options for the question. Look, this is also a question from 2019 JEE mains paper. So you know the angular width will be for Young's double slit experiment beta by capital D, and beta, you know, d lambda by small d, and here d is there, so it will be actually angular range of the fringes. Each fringe will be lambda by d. So we can find out what is the angular width of the fringe produced by this light, 500 nanometer light, and slit of separation 0.05. So lambda is 5 into 10 to the power minus 9. 500 nanometers. So along with that 100 multiplied. This is again millimeter, so -3. So finally, what you get is 0.01. This is in radian. This is in radian. So radian can be converted into degree. So if you want to do that, pi radian is 180 degree. So 1 means 180 degree by pi, and this much 0.01. So this will be 180 1.8 divided by 3.14. 3.14 pi. So if you look here, this will go, this is 90, this is this, and if we calculate it properly, this will come around 6 degree. That means 57 degree is the correct answer. Okay, so you have to remember this point. Lambda by small d is the angular range of a particular interference fringe, or in this case at least the brightness fringe, angular width of the fringe is equal to lambda by d. Okay, so this is how you can find out problems from here. One more last problem we'll take for today, and next I will rigorously concentrate on the diffraction part and also the polarization part. So this is from JEE Advanced 2014. So there are questions like this. So let us see how we can solve this problem. A light source which emits two wavelengths, lambda 1 is equal to 400 nanometer and lambda 2 is equal to 600 nanometer. So one source can emit two wavelengths, lambda 1, lambda 2, used in a Young's double slit experiment. So this particular source, if we use in Young's double slit experiment, then if recorded fringe width corresponding to, or for lambda 1 is beta 1, this is the fringe width, and for lambda 2 the fringe width is beta 2. If we can separate out and then find out the fringe width and the number of fringes for them within a distance of y on one side of the central fringe are m1 and m2. The number of fringes for them within a distance y1, within a distance y on one side of the central maximum are m1 and M2 respectively. So we have to find out whether that beta 2 is greater than beta 1, M1 is greater than M2, or for central maximum, third maxima of lambda 2 overlaps with fifth minimum of lambda 1, or angular separation of the fringe 1 is greater than lambda 2. So these are the options we have to solve. So first of all, we have two lights of wavelength lambda 1 and lambda 2. Lambda 2 has greater wavelength, that is 600 nanometer, and lambda 1 has smaller wavelength, that is 400 nanometer. Now let us see this question, this answer option. So we know beta is equal to d lambda by d. Okay, I'm sorry, it's just ulta. Capital D, d lambda by d. Capital D lambda by small d. So this is actually the fringe width. So if we have greater wavelength, but anyway the apparatus are same, so experimental arrangements are same. So that's why I'm not taking this and this. So beta is directly proportional to lambda. So then what will be greater? Beta 2 is greater than beta 1. That is true because this. Okay, so we can say from this relation beta 1, beta 2, beta 1. So beta 1 is greater than beta 2. That we can say. Okay, so mainly you have to remember that fringe is directly proportional to lambda, and beta also directly proportional to lambda. So that's why this is correct option here. Because beta 2 corresponding wavelength is 600 nanometer. Okay, anyway, this is beta 2. All right, we'll go to the next question. See, next question is saying that the number of fringes for them within a distance y on either side of the central maxima are M1 and M2. So if that is the case, then we can write M1 beta 1 is equal to M2 M1 M2 is equal to M2 B2. Okay, we know this. So if this is the case, so we can see that beta 1 is greater than beta 2, M1 is greater than M2, M1 is greater than M2 then. So M1 will be greater than M2. Okay. Now last part of this problem says, okay, so let us say anyway this, the angular separation of the fringes lambda 1 is greater than lambda 2. So theta is actually lambda by d. So angular separation of the fringes, this depends directly proportional to lambda. So this is not true. The angular separation is not true. Okay. For the central maximum third, and maximum of lambda 2 of the order fifth minimum each other. Okay, from central maxima, third maximum of lambda 2 overlaps with fifth minima of lambda 1. So then you have to prove whether it is true or wrong in this case. So we know 3 into 600 nanometer. So 3 capital T by small t into lambda. That means 3 into, see here actually third maximum we have told. So you can see 3. Okay, let me just go here. 3, 3 beta 1, suppose. Okay, 3 beta 2, sorry, 3 beta 2 is equal to 25 minus 1 capital D by 2D. So these are two things, and with lambda 1. Okay, so this is also beta 1. Actually, you know what you are getting, the thing you are getting is 3 capital D by small t into 600 nanometer. Okay, so this will be exactly equal to 'So from both sides this can go off. 6 and d by d, this will go away, and this 2. This is 9 by 2. So these are not actually, this is also not true options, because both sides will not be the equal. Okay, the question is that whether third maximum of first, that means with lambda 2 overlaps with fifth minimum of lambda 1. The answer is no. Okay, all right, so with this we'll stop it here for today. We have picked up only 4 questions for today, but we'll take up some more questions in the next class, where we'll be taking up mostly from diffraction and polarization, and if we get some questions on interference, that also will pick up. So for today it is this is all for today. We'll wind up today's discussion. Thank you very much.